Now let's come to one of the last projects in the series. This is called the Zun in China, and it's called CITIC Tower. And this introduced the mega frame, braced mega frame concept, completely different from what we have seen so far. We have seen the tubular concept, we have seen the braced tube, we have seen the bundle tube, we have seen the diagrid, and now we come to the braced mega frame system. So this is combination of several innovations. So let's see what is this, and it's composite. So you can see here, it's made up like this one. So you have a frame, I will show you later in a way. So it's, first of all, it's located in China, and it was constructed not long ago. At that time, one of the few tallest buildings in the world, because right now, tall building competition continues, and every building which is built, another one taller than that comes up very, very quickly. So it basically combined the concept of outriggers, combined the concept of mega frames from other projects. So it took many things from other projects and put them together to make it work. And one of the reasons why they needed all of that is, we will see. So first of all, according to the architecture or the tradition, the form had to look something like this, because this is the Chinese form that they wanted to make. Normally, you have seen tall buildings becoming smaller at the top because of the wind, minimizing the wind load. Every tall building, major tall building, super tall building is like that. But this one becomes bigger at the top to follow this traditional design. And it was in a zone 8, highest seismic zone in China, one of the highest seismic zones. So that means this was unlike many buildings which are designed mostly in wind prominent areas. You see the buildings in New York controlled by wind, Chicago controlled by wind, Dubai controlled by wind. Mostly tall buildings are Malaysia, 3 super tall buildings there, all controlled by wind, because earthquake isn't the primary concern there. But this building was different. This was also for wind and for earthquake. So the system had to be developed to handle both strong forces. And so it's very high, 527 meters, as you can see, 108 floors. And this is a large building, especially at the base and the top. So one of the problem was that they couldn't reduce the top size. So the mass at the top was heavy, not good for seismic. And also the size were very wide, not good for wind. But the value they got from large floor at the top by selling it at higher price outweighed the structural cost, because if you go up and the floors are larger, you get more high price selling space. So this is the structural form you can see here. So it was divided into almost independent small structures put in on each other. So you can think of this being constructed of these 7 pieces independently and put on top of each other. So the gravity load doesn't flow through the columns all the way. It keeps transferring to the outside mega columns through those trusses that you see, those outriggers. Normally they're outriggers, but here they are also transfer trusses. So those transfer trusses transfer the loads from each zone out to the outside columns to the mega frame, and then the mega frame is then further braced by these large diagonal braces for both lateral wind and earthquake. And then you have dampers further into that to control the wind and seismic drifts and demands. So it's a highly complex structural system consisting of so many components all coming together to solve this problem. So that's the currently one of the most complex structural system in the recent history, which combines so many forms together. And and they did, of course, a lot of wind studies, a lot of analysis, a lot of design. You can imagine how many studies must have been done to make this structure possible. And it used belt, it used outrigger, it used core, it used bracing, it used mega columns. So everything in the, like I say, in the menu, they selected and they put there. The steel concrete composite columns. So, you name it, and this building has it. So it's a combination of so many technologies all put together. And once again, Arab group designed the structure for this one. And let's look at how it looks like. So that's the core, the elevator cores. Then those are the mega columns around that. And then you have the mega trusses coming in. And then you have finally the outside. So that makes up the structural system beautifully. And in between, the floors are just suspended. They are not really carrying the load down. So you don't need columns inside. So it's a free space. That's the beauty of this system. Almost to the end. Once again, in AIT, we asked some students to look at how structure of this kind will work for a mid-rise building, not super tall, but 300-meter building, let's say in Philippines. So some students compared it. They found that it's still economical to design this compared to a conventional frame tube. So it still will work even for 300-meter building in a seismic and high seismic wind zone.